Hello everyone, welcome to trigonometry. This is the first lesson on trigonometry and we'll follow the standard order that is adopted by nearly all the textbooks I saw on trigonometry and precalculus. First, we're going to define a quantity called angle and we will use the radian measure as the main tool. And then, based upon that radian angle, we will define trigonometric functions. And in section 3 of this notebook, we will consider some special angles and study the values of trigonometric functions at those special angles. Other aspects of trigonometric functions like graphs will be considered in separate notebook. Okay, let's begin. Let's begin discussing angle, and this is where we begin. A unit circle, x squared plus y squared is equal to 1. Why is this a circle? Here it is. This program is randomized and x comma y is randomly selected from a point on a circle, and you have consequently randomly selected right triangle like this. But in any case, please make this observation. The hypotenuse of this red right triangle is always 1 because the radius of the circle is 1. Consequently, hypotenuse squared is 1 squared, that's 1. And then how about horizontal and vertical? Horizontal squared plus vertical squared will be x squared plus y squared, and consequently by Pythagorean theorem we have this. And x and y can be negative as well. In this particular case, when x comma y, this point is selected in first quadrant, then x and y are both positive. Let's run this program again. In this particular case, x is positive, y is negative. That's because we have the point on the fourth quadrant. And how about this one? X is negative and y is positive. That's because we have the second quadrant here. And in a third quadrant, x and y will be both negative if we get something in the third quadrant. Okay, we have it here. Alright, now that we talked about the unit circle, x squared plus y squared is equal to 1, let's define the angle using the radian measure. And here it is. We define the angle or the radian measure of the angle as the distance of the counterclockwise travel from the initial point 1, 0 to the terminal point x, y. Here in this visualization, the initial point 1, 0 is on the right hand side edge on the x-axis, and the terminal point is the tip of this arrow. And this program is randomized, so you can run this many times. And we have something like these. Okay, please make another observation here. In this measurement, we have this pi popping up. Why do we have that pi? Well, please recall the circumference formula of a circle. The entire circumference is 2 pi r. And in this particular case, radius r is 1, so the 2 pi is entire circumference, or the full revolution, 300-degree revolution. And half of that will be half circle, 180 degrees, and a quarter of that will be, so quarter of 2 pi will be pi over 2, isn't it? That's going to be 90 degrees. Let's see, do I get something close to 90 degrees or 180 degrees? Okay, we got relatively lucky here. The theta value is reasonably close to 1.5 pi, 3/2 of pi, or 3/4 of 2 pi. And as you can see, we have something pretty close to 270 degrees. And okay, we got lucky again. Theta is very close to pi this time, a little bit less. So what do we have? We have something very close to 180 degrees, a little bit less. Now what if we move clockwise? That's when we have negative angles. We're going backwards, so we have negative. It's easy. Another observation, the terminal point x comma y is periodic. As a matter of fact, it's a little bit difficult to see it this way. Well, let's represent it in this fashion. I put period in wrong place, kind of like this. X comma y for the angle theta plus or minus 2 pi is the same as x comma y for the angle theta. And here are some visualizations, and we have these two pictures on top where the left hand side is actually x comma y for the angle theta, and actually this one is actually the left hand side, and then the right hand side is x comma y for theta plus 2 pi, because you just went through one full revolution and then by theta. So we have something like that. And then another randomization, so we have another angle, but still the idea is the same. In the left hand side we have just angle theta, which is pretty close to 90 degrees, or about pi over 2, a little bit less than that. And then in the right hand side we have pi over 2 plus 2 pi, because 2 pi is 360 degree revolution. We end up with the same place. And the bottom two pictures show the case when theta is negative, and then theta plus 2 pi. So we have periodic behavior for the terminal points of those angles. Now, this is how we defined, this is how our textbook defined the radian measure of the angle. And then the way our textbook did is, now we have the angle, so define all the trigonometric functions, and then get everything done, and then go back to DMS measure, and the degree and minutes and second, yes, all those 360 degrees and things like those, and then define trigonometric functions there with all those triangles and geometry, and then come back and talk about trigonometric functions again for arbitrary circles. Basically, what our textbook author does is define and study trigonometric functions 3 times for 3 different types of angles which are supposed to be equivalent. I didn't really like this kind of approach because it's too complicated, so let's go a little bit further now so that our lives will be much easier later on. Instead of starting from the unit circle x squared plus y squared equals to 1, let's start from a arbitrary circle, not arbitrary circle, a circle radius r, where r is arbitrary positive number. X squared plus y squared is equal to r squared. And it's kind of like this. The same situation as before. X squared and y squared are horizontal squared and vertical squared respectively. And r is hypotenuse. So r squared is hypotenuse squared. So we have Pythagorean theorem again. Horizontal squared plus vertical squared is equal to hypotenuse squared. So we have x squared plus y squared is equal to r squared. Or equivalently speaking, x over r squared plus y over r squared is equal to 1. Okay, in arbitrary circle, we can define angle like this. Similarly, we define the angle as the travel distance of counterclockwise travel from the initial point r comma 0 to the right hand side to the terminal points x comma y, but divided by the radius r. And here's a visualization. We have circles with 2 different radii, and I didn't want to draw circles really too big, so I drew a unit circle with radius 1, and then a circle with radius r where r is a little bit smaller than that. And because I divide it by r, we end up with same angle, and as you can see here, the same the radial, terminal points are terminal points are located at the same radius. So same radial position. The starting point is r comma 0, and if you simply measure the travel distance, counterclockwise travel distance or counterclockwise direction arc length, and simply stay there, then we'll have different arc length for different radii. However, by dividing everything, all this arc length by the radius, we have the same quantity, and that's called the angle. And this kind of definition is a little bit more general and a little bit more useful. However, I have to say a little bit less precise, to tell the truth, because you have to prove, as a matter of fact, that the counterclockwise travel distance divided by r is actually constant, and then it corresponds to the counterclockwise travel distance for unit circle, and that's a little bit difficult to do, as a matter of fact. But then again, well, in first year college level, we skip a lot of proofs of difficult things, so why don't we just add one more like that, and instead we do trigonometry a little bit easier, and that's what I'm trying to accomplish here. Now if I move backward clockwise, then the angle will be negative, and that's something we saw before, the same deal. Now what if we do this disregarding the sign, whether plus or minus? Then what we have, the angle theta is travel distance, which is arc length over radius, isn't it? And we just drew away plus or minus sign. So if I do that, the angle theta as an absolute angle, then that's the same as arc length over radius, or s over r, where s is the arc length of a sector. Now move r to the other side, then we have this formula here. S is equal to r theta. We can find out the arc length of a sector by multiplying the radius and the angle, if the angle is radian measure. Neat. And remember this formula, please, because we're going to be using this kind of formula later on. Okay, we define the angle using the radian measure. We did it for unit circle. We generalize it for arbitrary angles. And let's make a comparison between the radian measurement and the DMS measure. And, well, here's a conversion formulae. Here are the conversion formulae, in plural. Radian angle can be obtained by DMS measure by multiplying pi over 180. As a matter of fact, it should have been 2 pi over 360, because 360 degrees is full revolution and 2 pi is full revolution. Full circumference is 2 pi r, isn't it? So we need 2 pi. After simplification, you're going to get pi over 180. And likewise, we can find that DMS measure from the radian measure by 180 over pi. So for example, here are some basic angles. If you have 30 degrees as DMS measure, then what is the radian measure of that? All you have to do is multiply by pi over 180, and 30 over 180 is 1/6, and then pi was there, so we end up with pi over 6. For example, what is 45 degrees? And that's 45 over 180 times pi, turned out pi over 4. And these, by the way, are standard angles, to tell the truth, and they are related to some special trig values. Let's see, do we have some pictures? Yes. Okay, this is for 30 degrees. And then, okay, this is just conversion from DMS 30 to radian pi over 6. And then this is for radian pi over 6 to DMS 30 degrees. Okay, it wasn't much of a deal. It was pretty much waste of time. What's important was the conversion formula here. Pi over 180 or 180 pi.